morning, dear students. I am Dr. Basavarajappa. I shall engage today's class with 18 Mat 653. It is the open elective subject for the 6th semester. The subject title is Linear Algebra and with the subject code as that is 18 Mat 653. To start with the introduction, let me share with all of you few points regarding this subject, that is linear algebra. Linear algebra, the topics completely deal with the applications of matrices, the preliminaries of the matrices, and then operations, mathematical operations on matrices and their applications in engineering. Especially the basics of this matrices already you learned in the previous semesters, that is even in the right from your lower level classes up to the engineering first year and second year degree level you have studied. And recalling all the fundamentals of this linear algebra, now we are going to study the next part of the matrix analysis, that is theory of matrices and then its applications for the engineering field. Yes, the first there are 5 modules. The first module deals with the introduction of the matrices, then system of linear equations, the consistency by finding the rank of the matrix, consistency and then inconsistency of the matrices, and LU decomposition to find the solutions of the system of linear equations. This is one topic in the first module. And in the next module, in the same module, the next topic is we deal with the algebraic properties on the matrices, that is vector spaces, subspaces, even dimensions, span and its applications at the end. So this is the first module, deals with the applications of matrices both in real number system and the algebraic treatment. So first of all, let us learn how this basics of matrices we have to share with all the basic definitions. Let me explain in the beginning, and how these matrices theory will be applicable in engineering, especially for 3 different applications as per the VTU syllabus. This goes for the applications. First application is graphs and networks, and second application is matrices in engineering, and third application is computer graphics. These 3 will go as matrix applications, that will be in module number 5. But as I told you that module number 1, the first is system of linear equations we have to study. System of linear equations through matrix theory. That means it needs the preview of all the matrices, basic definitions and their operations, and then we will go for rank of the matrix, and then we will go for consistency and inconsistency of the matrix, and then solution sets, and then LU decomposition. All these things I will try to cover within few hours. That means maybe 3 to 4, 5 hours I will have to take for to complete this. Then starts in the same module, that is vector spaces, which will cover the definition of vector space, and then what are the properties of properties and axioms of vector space, and then subspaces, linearly dependent and independent vectors, basis and dimension, coordinate vectors, computations concerning to subspaces and the problems. So these things I will include in the first module. Out of the total number of hours allotted to me, I will try to cover all these contents in the first module. And in the last module, as I told you, that engineering applications, that is graphs and networks. So graphs and networks means especially we solve the problems in the case of a flow of the current through the circuits. There we will write the codes for that electric circuit, and then we will form the matrix equations, and then we will study the values of the unknowns. That is graphs and networks. And the next one is, that is matrices in engineering. Matrices in engineering deals with the 3-dimensional planes, their parallel condition and then intersection condition and overlapping condition. So these 3 conditions I shall explain in the second application of this module number 5. And module number 4, that is computer graphics. In this computer graphics we study with respect to the vertices and particular diagram, whatever it is given, nodes and vertices. In that, how to study the graph theory with the use of these matrices, and how it is to be colored, coloring of those lines, and then we have to count, and then we will have to put in the form of matrix equations, and then we have to solve. So this is what the material I am going to discuss in the next allotted time from VTU, that is in advanced linear algebra, that is 18 Mat 653. I shall start with the first module, and all the preliminary, that means basic definitions of matrices I shall introduce, and then I shall start how to find out the rank of the matrix, then how to find out the system of solution of the system of linear equations by studying all the possible cases. The possible cases means there exists a unique solution, there exists infinitely number of solutions, and there exists no solution. For what conditions these matrix equations will give us, how these a system of equations will give solution, how these system of equations will not give the solution, and how the system of equation will give infinitely many solutions. Under what conditions we are going to solve, that is nothing but comparison of rank. Comparison of rank from the coefficient matrix and the augmented matrix. Rank of the coefficient matrix is what, and rank of the augmented matrix is what. So then we will compare, and then we will see that solution exists or solution does not exist, even though solution exists, what kind of solution, that is infinitely number of possible cases we have to discuss. This comes in consistency, and then it is a solution. And next is LU decomposition method. This is a very special method in engineering, which will give us the idea that product of two triangular matrices, one is upper triangular and the another one is lower triangular. When you take a product of these two, then we will have to introduce the lower triangular matrix in the form of unit lower triangular matrix, and the upper triangular matrix without 1, 1, 1 on the principal diagonal. So these two matrices are to be clubbed as a multiplication, then we will separate the values. Afterwards we will use three important steps how to evaluate the values of the unknowns. Okay, let me start with the first module. What are the basic definitions we deal with in the case of matrix theory? That means consistency and inconsistency of system of linear equations. Okay, so the subject name is advanced linear algebra, 18 Mat 653, then module 1 and module 2. Module 1 deals with the system of linear equations. Linear equations, vector space, and so on. And module 2 deals with applications in engineering. Advanced linear algebra, that means linear algebra applications in engineering. There are three applications, that is graphs and networks, matrices in engineering, and computer graphics. These are the main topics we study in the next few lectures. Now I shall start with module 1. In this module 1, system of linear equations using matrices. Let us discuss the basic definitions of matrices. It is only the recapitulation of all the definitions what you learned in the previous syllabus, that means in the lower level classes. I will just give the hint of that, and then I will proceed to the exact syllabus whatever in this 653 it is allotted to me. Now I shall start with preliminaries of matrices. Preliminaries of matrices means it will cover all the definitions of matrix. That means you have studied determinant, now the next part is matrices. Okay. So what is the meaning of matrix and what is the use of matrix in engineering and how it is represented and what are the definitions? To start with the solution of system of linear equations, we do require all this basic knowledge. Okay. The first one, definition. Matrix you can take with the symbol, that is big square brackets, and why this is to be chosen? Because it is the array of numbers which are arranged in the form of rows and columns. Okay. It is an arrangement preliminaries of matrices. It is an arrangement, definition of matrix I am writing. It is an arrangement of elements, we call them as numbers, as rows and columns. Rows and columns. We call that rows by the general symbol as m number of rows, and then columns as n number of columns. That means here rows you can call it as small m. This is common symbol, everyone is accepted, that is m rows and n columns. Okay. So let A is equal to, if I write the matrix A11, A12, A13 and so on, that is A1n. Then next row, this is called first row, that is called R1, then A21, A22, A23 and so on. This is A2n, this is called row 2. Similarly, that is A, M1, A, M2, A, M3 and so on, A, M, N. This is R, M. First row, second row and mth row. This is called M cross N matrix. This is the way of representing number of rows and number of columns. This is first column, you can call it as C1, this is C2, this is C3 and so on. This is row 1, this is row 2 and this is row M. This is column C2, then Cn, that means last column. So that M cross N always will be taken for a particular number. That means it may be M equal to N, it may be M is less than N, it may be M is greater than N and M is not equal to N. So all these possible cases we discuss with the general matrix. This is general matrix. So matrix with the square brackets, this is one way of representing. Otherwise, there are three symbols of representing matrix: thick brackets and double bar. So any one of these three symbols we represent to arrange the elements or the numbers inside this in the form of rows and columns. Okay. So A11 we call for any process, A11 we call for any process. For example, in the case of row operations in the same matrix theory, we call it as pivotal element. This element is called leading element, otherwise it is called pivotal element. Okay. So when this is pivotal element means, and this diagonal representation is called principal diagonal. This is called principal diagonal. So principal diagonal above and principal diagonal below, we define two types of triangular matrices. one is lower triangular and the another one is upper triangular matrix. Okay. So, upper triangular and lower triangular, from this we will define, and the related definitions we are going to define one by one after this. The first one, related definitions, I shall discuss with reference to the general matrix. The first one, row matrix. From the same example which I had written, row matrix can be taken as A is equal to the first row, A11, A12, A13 and so on, A1n. That means this is called number of m rows and n columns. M rows and n columns means this is m rows and n columns is equal to 1 row into n column. Only one row is there. Therefore, in place of m I am writing it as 1, and number of columns means total number of columns are n. Next is column matrix. So, column matrix means A is equal to A11, A21, A31, AM1. This is column matrix. Here m rows, n columns is equal to, that is m into 1 column. That is m rows means totally A1, 2, 3 and up to m. This is m number of rows, and n number of columns means only 1 column is there. So that m cross n is equal to m cross 1. And the third one, square matrix. In this square matrix, example, consider 3 cross 3 matrix. That means m cross n is equal to 3 cross 3 implies m is equal to n is equal to 3. This is number of rows is equal to number of columns, that is equal to 3. Therefore, A is equal to A11, A12, A13, A21, A22, A23, A31, A32 and A33. This is number of columns means R1, this is R2, this is R3, this is C1, C2, this is C3. That means m is equal to 3 and n is equal to 3. Therefore, number of rows is equal to number of columns, that is called square matrix. And the next one, non-square matrix. So, non-square matrix means number of rows is not equal to number of columns, or vice versa, number of columns is not equal to number of rows. So, example, in this A is equal to A11, A12, A13, A21, A22, A23. This is one sample, and another sample, that is A11, A12, A21, A22, A31, A33. How do you represent this one, non-square matrix of the type? First, it will be represented as m rows and n columns. That is m cross n is equal to 2 rows and there are 3 columns, and here 3 rows, m cross n is equal to 3 cross 2. In the previous case it is 2 cross 3 and this one is 3 cross 4. Both are non-square matrices. And next is diagonal matrix. So diagonal matrix will be actually whatever the general matrix I have written, even with the same example, if I take this one, diagonal matrix A is equal to A11 0 0 0 A22 0 0 0, this is A33, then this is called diagonal matrix. This is called diagonal matrix means elements above the principal diagonal are 0 and elements below the principal diagonal are 0. That means this is, these three elements are 0 and these three elements are 0. This is called diagonal matrix. And unit matrix. Unit matrix means A11 is equal to A22 is equal to A33 is equal to 1 in the above matrix. That means A is equal to 1 0 0 0 1 0 0, this is 1. This diagonal matrix takes the values A11 is equal to A22 is equal to A33, that is equal to 1. That means diagonal matrix and unit matrix both are having the elements above the principal diagonal are 0 and elements below the principal diagonal as 0. That means here they are 0 but not 1 1 1, that is called diagonal, but 1 1 1 it is called unit matrix of the same type. And next, that is symmetric matrix and skew symmetric matrix, null matrix, like that. Next definition is null matrix. What is null matrix? In the same example, if I take A is equal to 0 0 0 0 0 0 0 0, all the elements inside the matrix are denoted as 0, it is called null matrix. Next, symmetric matrix. That means if Aij is equal to Aj, then it is called symmetric. Then the example for this symmetric matrix will be taken as, that is A is equal to AHG, some numbers you can also allot, BF, then G, this is FC. Here what we are going to do with respect to this symmetric matrix, rows and columns will be interchanged. Rows and columns will be interchanged means the matrix should remain the same, then only we call it as symmetric matrix. Then if it is symmetric matrix means Aij, Ij means I is for row and J is for column. Then if you interchange, that means Aij is equal to Aji. Suppose this is the first row, this is the second row, this is the third row. If you interchange, that means this is C1, C2 and C3. This is column 1, 2, 3. When you interchange the rows and columns, if the matrix remains to be same, we call it as symmetric matrix. AHG will come as AHG only, HBF will be HBF, it will be same, and GFC, that is GFC here, G will come here and F will remain here and C will remain in the third column, that is last element, third row, that is last element. So in the case of row and column, this happens to be the last element. Therefore, if Aij is equal to, that means now it is not just interchanging, you have to interchange the rows and columns, then if the matrix remains to be same, we call it as symmetric matrix. And next definition is skew symmetric matrix. What is the meaning of skew symmetric matrix? The meaning of skew symmetric matrix with reference to this symbol, that is Aij is equal to minus of Aji. This is the interchange of these two. Aij is equal to, here leaving the plus sign, here leaving the minus sign. If the matrix changes its sign after interchanging the rows and columns, then it is called skew symmetric matrix. I shall write the example for this also, how this skew symmetric matrix will be taken. That is, A is equal to, for the example of this case, A is equal to, should be 0 H minus G minus H 0 F and G and minus F, it is 0. Then you can also take this one. This changes its sign when Aij, the elements inside, this is equal to Aij, and if it is equal to Aji with minus sign, then it is called skew symmetric matrix, because this will happen here and this second row will go like this, and second row will go in the second column and third row will go in the, that is third column, okay, along with minus sign. Then it is called skew symmetric matrix. Now the next part is upper triangular and lower triangular matrix. Upper triangular matrix. What is the meaning of upper triangular matrix? As I told you already in the example, that is the same example you can consider 3 cross 3. Let A is equal to A11, A12, A13, 0, 0, A22, A23, this is 0 and A33. This is called upper triangular matrix. Upper triangular matrix means this is the matrix below the principal diagonal, the elements are 0. That is lower triangular matrix in the opposite type of this one we are going to write. That is lower triangular matrix. Lower triangular matrix means let A is equal to, that is 0, sorry, A11, this is 0, next is 0, A21, A22, this is 0, A31, A32 and A33. This type of matrix in the square matrix, this is called lower triangular matrix. That means lower triangular meaning is the elements below the principal diagonal are not 0, but the elements above the principal diagonal are 0. This is called lower triangular and this is called upper triangular matrix. That means here it is very clear whenever we say that because this concept we are going to use for LU decomposition method in the same module, I will be using this concept and all the definitions we will take it into consideration when we analyze and we implement the meaning of matrix. And the next one is transpose of the matrix. Next definition, transpose of the matrix. Transpose of the matrix is nothing but you have to interchange rows and columns, that is denoted by A transpose, like AT or A dash. Any one symbol you can follow and both the symbols are accepted, A dash or AT. For example, if I write the general 3 cross 3 matrix, then how this is to be transposed? A11, A12, A13, A21, A22, A23, A31, A32, A33. So A transpose is equal to A dash, any one symbol you can write. This is the first row, will be written as first column. second row will be taken as second column, third row will be taken as third column. Otherwise, first column will be written as first row, second column will be written as second row, and third column will be written as third row. Interchange of rows and columns with the same elements inside the matrix is called transpose of the matrix. Now I shall write, that is A11, next is A12, next is A13 in place of this, and A21 will come here and A22 will remain there itself, and A23 will be the third element in the second column, and A31 and A32 and A33. So this is called transpose of the matrix. Here one property we discuss after writing the transpose of the matrix, A transpose and whole to the transpose is nothing but A only. This is the very important property we will use in the vector space and also the algebraic treatment of these matrices in the next discussion, and this property I will be using. A transpose whole to the transpose is nothing but the original matrix, otherwise A dash and whole to the power dash both are same. Any one notation you can discuss. Now what is the product property? If you come across two matrices, then how you are going to explain the product? But in the case of this transpose, the product is A into B. I will write it as a note for your application meaning of this matrices definitions. A into B whole to the power transpose is equal to B transpose first and then the A transpose. It is not A transpose into B transpose. This is nothing but B transpose first. That means second matrix will come as the first matrix with the transpose, and first matrix will go as a second matrix with the transpose. So this is the property, and this is the first one. And ordinary product, multiplication of the product of the two matrices is not equal to A into B is not equal to, that is B into A. That means commutative law does not hold good in this algebraic property, that is commutative law does not hold good, because you can take an example for A, matrix A and matrix B, and matrix B whatever it is there. If you take for example in the real number system 2 into 3, A equal to 2, suppose A is not a matrix, B is not a matrix, A equal to 2, B equal to 3 means it is 6, this can be written as 3 into 2. Here this is holds good in the real number system product, but in the matrix it is not going to be valid. It is not going to be valid means product A into B is not equal to B into A, means algebraic property which we say that, which we claim that it is a commutative property, does not hold good in the case of matrices. Now the next part is to find out the inverse of the matrix. We have to find out the adjoint of a square matrix. What is the adjoint of a square matrix? For any matrix using cofactors method, we find out the inverse of the matrix, because inverse exists only for square matrices. Okay, so that is very important concept, that the matrix is invertible either by cofactors method you can do, or by elementary row operation, which I am going to explain now. But the basic method is, we call it as cofactors method. So inverse of the matrix, you remember this exists only for square matrix, not for non-square. Square matrix means what? Square matrix means M equal to N. That means it will be 2 cross 2, it will be 3 cross 3, it will be 4 cross 4, like that. That means M equal to N. Number of rows is equal to number of columns. Therefore, inverse of the matrix exists only for square matrix. Then there are several methods we can find out. One is cofactors method, second one is Gauss-Jordan method, and third one is Cayley-Hamilton's theorem we apply. There also we calculate, and the partition method we apply, and another one is using identity matrix. So these are all the methods where we can discuss about the inverse of the square matrix, and the basic method is using the cofactors calculation. How these cofactors calculate? This is the very first method, cofactors method, but this method has got the limitation. This method cannot be applied for all the matrices even though it is given as square matrix. So what is the inverse of the matrix? Now if A is the square matrix, if A is the square matrix, then its inverse by cofactors method, cofactors method is given by A inverse is equal to adjoint of A divided by determinant of A. This is a very important equation. A inverse is equal to adjoint of A divided by determinant of A. What is the meaning of adjoint of A? Adjoint of A is nothing but transpose of cofactors, where adjoint of A is equal to transpose of cofactors of matrix A. Cofactors matrix A. What is the meaning of cofactors? Cofactors of the matrix A means, suppose A is equal to, example I am taking, A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33 for this adjoint, then it is 3 cross 3 where it is equal to m cross n, that means it is a square matrix. Then adjoint of A means what we calculate here, we will go like this. First cofactor is calculated with plus sign here, second cofactor with minus sign, third cofactor with plus sign, and fourth one like alternately plus minus. This becomes minus, this becomes plus, this becomes minus, this becomes plus, this becomes minus, and this becomes plus. How the cofactors are going to be calculated? In place of A11, we calculate the determinant of these 2 cross 2. That means we call it as a minor. This is major. This is major means 3 cross 3. Its minor order. Major order means 3 cross 3. Order is equal to 3. Then minor order means that is A22, A23, A32, A33. The determinant of this 2 cross 2 will become the first cofactor value in place of A11 with plus sign. Next, that means why we are chosen like this means, when you want to write the cofactors in this cofactor in this position, then you have to ignore its corresponding column and you have to ignore its corresponding row. That means this row is to be ignored and this column is to be ignored. So now I am going to calculate this one with minus sign. Then cofactor in place of this A12, then I will ignore the middle column, then I will ignore the first row, then I will take these two for the determinant. If I want to calculate this, I will ignore this last column, I will ignore the first row, like that. So if this is equal to A1, B1, A1, B1, C1, A2, B2 and C2, A3, B3 and C3. These are the cofactors. Okay, this is the matrix given, sorry, this is capital A, and this is the matrix given, but this is the cofactors matrix. Okay, with cofactors and without cofactors. Now, this implies adjoint of A is equal to A transpose. Adjoint of A is equal to A transpose. A transpose means you have to write this row in the form of column. That is A1, it is B1, it is C1, A2, B2 and C2, A3, B3 and C3. This is the adjoint of the given matrix in terms of cofactors. Now the inverse of this matrix A with the determinant. That means determinant means the determinant symbol is applied to this A, provided this is very important condition, if and only if determinant of A, this is nothing but triangular shape we represent, this is not equal to 0. This is the main condition. Determinant if it is 0, then this method fails. If the determinant is not equal to 0, then this method is applied. This is the main goal of applying, main goal of studying the cofactors method to find out the inverse of this matrix. So this part is very important, you remember, because I will be using this in the case of matrix which is invertible. There I will use this concept in the vector space, and the subspace also there I will be taking, even in the application also I will be taking. So this is regarding inverse of the matrix. Now I shall go for the very important discussion after understanding all these things. The first claim which I am going to solve the problems in the next class, maybe first you will have to understand the rank of the matrix, rank and then elementary row operations. So these two things will play the major role in all my discussions in the forthcoming classes. Now, what is the rank of the matrix and how it is to be calculated, and rank is going to be represented for which matrices and how the ranks are going to be verified. So this is our next part for understanding the rank of the matrix. Now, suppose I take the first matrix with the number of rows and number of columns as 3 cross 3, then rank of the matrix is said to be with that particular number it is given. Let A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. What is the order of this matrix? Order is nothing but the number of rows and number of columns, the value of M. That is anyway square matrix. That is, it is a square matrix. If I consider, for example, this is a square matrix, this is equal to 3 cross 3. That means 3 is the order here. Highest order of the matrix is 3, highest order. Now, maybe in the next example I will take non-square matrix. But how to calculate the rank for the square matrix and for the non-square matrix? For example, non-square matrix A11, A12, A13, A14 like that, A21, A22, A23, A24, that means one more column I am extending, A31, A32, A33, A34. This is 3 rows and 4 columns. Now, listen carefully. This is the important meaning that we must know while solving the problems for consistency and inconsistency. Here, rank may be equal to this number, which is the square matrix. Here, rank may be equal to this number 3, but not equal to 4. Here, rank may be equal to 3 or less than that. Here, rank may be equal to 3 or less than that, but rank never be equal to 4. Remember, in the case of non-square matrix, the highest number will not become the order of the matrix, but in the case of square matrix, the rank may be equal to that number or less than that number. But here rank may be equal to 3 or it is less than 3, not equal to 4. This point you must remember. Okay. So now how you are going to put it in the form of mathematical sentence? Rank is nothing but the order. If I take this 3 is equal to R, then I will put in the form of definition. Rank of A is the order of the matrix when there are two conditions I am going to impose. The first condition, it has at least one non-zero minor of order R. And second condition, every minor of order higher than R vanishes. Well, what is the meaning of these two conditions which I imposed? One is, because for my convenience I have written like this, it has at least one non-zero minor of order R. What is the order here? 3. Here order is 3 or 4, but in the case of rank, order is not equal to 4 in that case. Okay, but here one non-zero minor. Now this is not a minor. As it is not a minor. It is the order given as 3 only. Minor means lower square matrix. Lower square matrix means this is 3 cross 3, and lower square matrix means it is 2 cross 2. Then 1 cross 1. It should not be equal to 0. That is what the meaning. It should be equal to minimum 1, and maximum is whatever the order is given. Maximum is whatever the order is given, and minimum should be 1, but it is not equal to 0. Therefore, this is the meaning. Non-zero minor of order. It cannot be 0. That means it must be minimum as non-zero number, that too it is equal to 1. And second condition, every minor of the order higher than R vanishes. Suppose you are going to represent R. For example, here it is not equal to 3. That means I will show in the next discussion how it is to be calculated. So if it is equal to not equal to 3, then it may be equal to 2. That means 3 vanishes. R equal to 3 vanishes, but 2 remains. Suppose it is not equal to 2, then 2 vanishes, 1 remains. This is called minor order, and order higher than R vanishes. This I will try to convince by taking example. In the first problem itself, all these things will be very clear. Thank you.